Welcome to Frontiers 4. I'm your host, Sidh Sikka. I'm the head of operations at Manifold, and I'm also one of the co-founders. But today is a little bit of a unique day because I'll also be your speaker, and so I'll introduce myself in that capacity as well. So I'm a Ph.D. student at Purdue. I'm working on the aeronautics and astronautics. I'm working on space robotics specifically. Um, my research is primarily focused on swarms of space robots that are for logistic tasks, things like repair, retrieval, assembly. Working towards a future where uh, autonomous swarms of space robots can sort of rescue you if your spaceship gets stranded, in orbit of Jupiter or something like that, uh, without having a situation like the story The Martian happen. So that's like the ultimate vision for the future. In the meantime, I'm working on control algorithms that are for these multi-agent systems. And so today, I will be talking to you about some of the work that uh, we've done at Purdue in the Ames lab. Oh, sorry, one more thing. I work under the guidance of Dr. Shaoshuai Mou. He's the head of the Ames lab at Purdue and also of the ICON Institute, which is the Institute of Control and Optimization over Networks. So a lot of multi-agent sort of heritage going on in my research career, and I'm pointing all that multi-agent stuff towards space robotics specifically. So today I will be presenting two things. One of them is some recent work from our lab on cooperative transportation of an object in orbit. And the second one is a project that's ongoing at Manifold. It's in early stages, but there's a lot of rapid, exciting progress there, which is focused on modular, self-assembling space structures. So let me go ahead and jump right into it. The Yeah, so as I mentioned, first I'll be covering optimal cooperative on-orbit object transportation, why we want this, why we need this. Those are two separate reasons. I'll be talking about the problem of interest um, and the sort of naive approach, like the first cut approach that someone can use. I'll be talking about the key idea of our approach and how our approach works mechanically, and then some extensions for this project that we're working on actively and in the near future. So that's for cooperative transportation of a single object in orbit. And then the second topic of the talk will be modular self-assembling space structures, like I mentioned. So I'll talk a little bit about the future of space structures, why this is a important research direction, some existing approaches and philosophies. This is a very new and sort of unexplored research direction, technological direction, really. And so there are many diverse um, philosophies about how to tackle this problem of modular self-assembling space structures. Not that many papers in this area yet. It's a relatively underexplored area, which makes it more exciting. And then what our goal is with this project, as well as the problem of interest that we're looking at as part of the Manifold project. And it's not fully finished yet in its fully rigorous form, but there's enough of it out there. We've put enough of it together to sort of describe what we're trying to do. So I'll explain that and the next steps for this project. So those form the contents of this talk. Let's just jump right into it then. And let's talk about why cooperative transportation of objects in orbit. Why is this important? So before we get to the graph that's depicted on screen, there's a reason why we want this capability. And that reason is for transportation of a payload from a lower orbit to a higher orbit or some assembly operation, some cargo transportation purpose. But that's not the primary reason why we need on-orbit object transportation. The primary reason that we need it is because of space debris. So, uh, low Earth orbit, all orbits of Earth, but especially low Earth orbit, is especially crowded with debris, with junk, space junk. You may or may not have heard of this problem before, but eventually this space junk can result in a problem called Kessler syndrome, where the junk starts colliding with other junk and creating more junk, and then trying to go to orbit becomes like flying through a rain of bullets. Um, so, according to projections, removing the 50 largest pieces of space debris can have billions of dollars of impact on potential risk mitigation in the future. But removing these removing these large pieces of space debris um, alone, like with a very inefficient method, is not enough because if the cost of removing the space debris exceeds the marginal benefit of removing it, then there's no point in doing it. It'll be very difficult to um, push any groups to remove the space debris for any reason other than sort of space activist reasons, right? We need to make it profit positive. And so any approach that tries to remove these large pieces of space debris should be fuel efficient because propellant is one of the most expensive parts of any space mission. It should avoid plume impingement. This is a problem where um, if you point your thruster at another spacecraft, you will damage that spacecraft. And the architecture should be multi-agent. So this is more of an opinionated take, but the argument in favor of multi-agent architectures is that they're inherently resilient to damage. If you have a single agent architecture, as soon as something happens to your single agent, the mission is over. But if you have a multi-agent architecture or even a swarm architecture, which is a large multi-agent architecture, then you get the benefit of resilience. Two, three, four agents can go down and the system will continue operating. And so all three of these things can make an approach for object transportation on orbit economically viable. And so we're looking for something like this. So our problem of interest is essentially as follows. We want to cooperatively transport an object with n agents rigidly attached to that object. We want to move it from some state A to state B. Now, there have been prior approaches to this problem. Cooperative orbital object transportation has a rich literature background, and cooperative object transportation in general has a very rich um, literature background. The problem of cooperative box pushing or cooperative object transportation has been addressed with drone systems, with terrestrial robots, but space poses some unique challenges. There are some good approaches that exist in the literature. These are decentralized approaches. So, in a sense, these are truly swarm. Agents only operate based on their local laws, and by doing so, they're able to cooperatively transport the object from point A to point B. So, in the literature, some of the notable methods that have been tried are a decentralized PD approach. So, just using a proportional derivative controller, which is one of the classic sort of controller architectures in classical controls theory. A controller that was invented 100 years ago is very robust, is in every system, from cars to coffee machines. So, in this study, these researchers essentially assigned a PD controller to each agent and showed that if each agent follows its own PD control law, they can cooperatively transport an object. So this is one method that exists in the literature. Another one, which is quite clever, is agents push only when they cannot see the target. So this is called an occlusion-based approach. By doing this, you create a nice distributed control law where the agents will eventually push the object to the target. And then there's also formation control approaches. So formation control is a rich area in multi-agent systems. And it turns out if you ignore the object, but you have the agents maintain a formation with some unknown resistance, something is uh, affecting their dynamics, it's the object, but we're ignoring it, then you can apply some of these distributed formation control approaches to transport an object from point A to point B. However, none of these approaches are optimal. Fuel is a very important resource in orbit, and currently refueling operations are not sustainable at all. So you really need to save what you have. And so optimality is a key objective of our project. of this project. Optimality cannot really be achieved with a decentralized or distributed approach. Really, you need a sort of centralized um, processor to do this model predictive control and calculate the to optimize the trajectory in question. But there are challenges with that, and we will get into that. So our just to cover a few preliminaries for the problem of interest that we're talking about here, we have one constraint, which is that our thrust vectoring should not be outside of some allowable angle. This is important because earlier, remember, I had said that we don't want plume impingement. We don't want thrusters pointing at the object that we're transporting. Um, and so some of those decentralized approaches don't respect a constraint like this, but we want to. This is another reason why um, an optimization-based approach, a centralized optimization-based approach, holds some significant advantages. It allows you to respect constraints like this. Okay, so this is one of the constraints that we were looking at in this work. And the sort of key problem that we're looking at is designing an optimal control strategy that respects these important constraints. Okay. One more sort of preliminary thing that I need to go over before we get to the problem of interest is what are the dynamics of the scenario that we're talking about? So to state it a little bit more rigorously, we are assuming that each agent has a thrust. We're calling that the capital U vector. And so the stacked vector of all the agent's thrusts over all time steps, that is the capital U vector, and that sort of represents the control vector that we are trying to optimize. And each agent, the system at a given time step has a certain position, which is the position of the payload in question, velocity, and attitude. The attitude is the sort of pointing of the object. So what's the angular sort of orientation of the object? And the angular velocity. And each agent is attached to the object via some attachment vector, which is the vector that points from the center of the object out to the center of the agent. So our state at any given time step, the complete state is those four things for the object, and then all of the attachment vectors for each agent. So what is the position of each agent relative to the object? And with that state, we can sort of characterize what the dynamics of the scenario are. So this looks a little bit complex, but I'll just quickly run through it. It's not so bad. Basically, we're saying that the next time step, position and velocity, are the previous time step's position and velocity plus the sort of relative orbital dynamics. That's what this phi matrix is, and plus the influence of the thrust from each agent on the payload. And so that is the position and velocity dynamics, and then the attitude of the object or the angular sort of orientation evolves according to some function of the angular velocity, which makes sense, right? The angle orientation will change depending on the angular velocity of the object, and the angular velocity of the object changes depending on the angular velocity of the object. This is Euler's rotation equations, plus the torque that is applied by the agents on the object. Okay, and then the agent's attachment vectors rotate with the object. That's what this last statement is saying. And so this is the complete dynamics of the scenario. The agents are able to apply, by using their thrust, they're able to apply a force and a torque on the payload. Okay, so that brings us to the problem of interest. So formally, the problem of interest is as follows. The objective is to minimize the sum squared cost over this entire U vector. This represents the sort of fuel cost of the scenario while respecting the dynamics of the situation and our thrust angle constraint. So this constraint is saying that the sort of pointing of your thrust must be aligned with the agent. And so this is our thrust angle constraint that we covered earlier, while taking the payload from state A at time 0 to state B at time t, where states A and B are your desired initial and desired terminal states of the system. So this is what we want, right? We want to we want to create a control input trajectory that will move the object from state A to our desired state B while respecting the dynamics, while respecting this thrust angle constraint. And if we're able to do this, that would be great. That would solve this problem. So why can't we just solve this? Why can't we just throw this into a solver? This problem is non-convex, and what that means is that there are many local minima and maxima, and the sort of landscape of this of the solution landscape is not nice, to use a non-rigorous math term. But really, it's not convex. And according to Malyuta and Yu, who published a study in 2021, any problem that is non-convex cannot realistically be solved in real time in space applications. So we need a convex problem to solve in real time. Okay. So that brings us to the key idea of this work. And the key idea here is pretty simple, actually. We want to take that original nonlinear problem and split it into two problems. And we can do that because the position and velocity of the payload only depend on the force applied to the payload. And the angle and angular velocity, the attitude and angular velocity applied to the payload only depend on the torque that's applied to the payload. Okay, so if we were able to formulate the force and the torque separately, then this would become two separate problems. One for position and velocity, one for the attitude and the angular velocity. Of course, they are linked. The same agent's thrusts produce both the force and the torque that's applied to the object. Okay. And this is sort of restating what I just said in math. So the position and velocity only depend on the sum of the agent's forces, and the evolution of the angular velocity and the attitude only depend on the sum of the agent's torques that are applied on the object. And we can relabel this as a variable tau k, torque, the torque applied to the object. So that allows us to separate into two problems. One is a nice convex inner problem that only deals with the position and the velocity of the object. And we assume a predefined torque trajectory is being applied to the object. So this problem is given a predefined torque trajectory, like let's say it's just defined somewhere else. Find the lowest cost agent forces such that the object gets to the desired position and velocity, and the applied torque matches that predefined torque that we supplied it as a parameter. Okay, so this is like the inner problem. This problem is convex. It can be solved very fast by solvers. The outer problem is non-convex. It says find a torque such that the attitude and angular velocity dynamics and constraints are satisfied. And then the outer problem is to iteratively improve that torque such that the cost of the inner problem keeps decreasing. Okay, so every time that we tweak the torque trajectory, we resolve the inner problem and find what the best possible agent forces are given that torque trajectory. This is the bi-level formulation of this problem. So these are the inner problem and outer problem more formally stated, um, which is pretty much a repeat of what we had earlier. Okay, so to solve the inner problem, we use convex optimization techniques. Specifically, we use the splitting conic solver and the interior point optimization solver. The interior point optimizer is actually a non-convex solver, but we use it for comparison in this work. And then for the non-convex optimization, we can't use any nice convex optimization technique. In this work, we use heuristic algorithms, genetic algorithms, and particle swarm. These algorithms are well suited for exploring non-convex solution space. And so that's what we use. Okay, so just to summarize the method that I'm describing. Um, First, we generate an initial population of torque trajectories. So these are just randomly generated torques. And we then project it into the feasible space, meaning we take each of these torque trajectories and we find the closest torque trajectory that would also satisfy the attitude, angular velocity, constraints, and dynamics. So we just do a least square sort of projection. We optimize the inner problem, like we solve the inner problem for each of those projected torque trajectories. And then we improve the torque trajectories using some heuristic algorithm, in this case, genetic operators and particle swarm operators. So we just tweak those torque trajectories depending on what the inner problem cost was. And after doing some many iterations of this, we output the best torque trajectory we found by doing this process. Okay, so now the feasibility projection, I didn't talk about that yet, but I sort of glossed over that when describing this, but we should explore that more thoroughly. Basically, given some randomly generated torque, we need torque trajectories that satisfy the constraints from the original problem. And so all we do is we just solve this. This problem is non-convex, but it solves fast in practice because the objective is very simple. It's a quadratic objective. We're basically just finding the closest, least squares closest trajectory that satisfies the constraints um, to whatever randomly generated ones that we had. And the way that we update the population after we solve the inner problem for each of those trajectories is we rank the torque trajectories according to the inner problem cost. To rephrase that, we essentially solve the inner problem for that torque trajectory, and then solving the inner problem means finding the best agent inputs that match that torque trajectory. And so we solve that over and over again. Uh, and each cost basically represents what the best agent control inputs could be for that given torque trajectory. And so you can imagine if we then improve the torque trajectory, we improve the agent control inputs. So we use these based on the cost, we rank those torque trajectories, and then we use genetic selectors and particle swarm optimization methods to improve the exploration of the potential torque trajectories, uh, the exploration of that space. And we just keep iterating that, and those torque trajectories get better and better over time because of the way that genetic algorithms and particle swarm optimizers are able to explore that space and iteratively improve. Okay, so in our simulations, we found that when we compared the our bilevel approach, our population-based bilevel approach, to just putting the problem of interest into a nonlinear solver and just letting it do it, we found that, no surprise, our method was superior. Otherwise, there wouldn't be a paper on this. And particularly, we found one really notable benefit, which is that our method very quickly finds a low cost trajectory, whereas the NLP solver can take a long time to even start to find low cost trajectories. The reason for this is because by doing this bi-level stuff, we're basically creating a warm start by generating a random trajectory, projecting it so that the torque trajectory satisfies the constraints, and then giving that torque trajectory into the convex solver. We're kind of doing a warm start approach. We're basically generating a warm start for the situation. Whereas the NLP solver has to solve all constraints of the problem from some very cold start, like all zeros, and it's just not able to do that in a reasonable amount of time. Uh, we didn't find a significant difference between the genetic algorithm and the PSO performance. I know here it says that there is some difference. The PSO was better. Generally, that was a little bit true, but statistically insignificant for the number of tests that we ran. And I have this little animation here which shows the agents moving some irregularly shaped object through space. You can imagine some thrust plumes coming out of the back. I didn't get the chance to animate those thrust plumes, but essentially this is what they're doing, right? They're firing their thrusts and cooperatively moving an object from some initial position, velocity, and angular state to another position, velocity, and angular state. Okay, so just to conclude this section, there are some distinct advantages to our approach over the baseline. So one is the thing I said, which is within a single iteration, because of this warm start, uh, we're able to generate a feasible solution to the problem. It's not optimal, but we're able to generate a sort of low cost or feasible a solution that satisfies the constraints. It doesn't violate the constraints of the situation. So in a space situation, if you need to move that object quickly and you need to calculate a trajectory quickly and you can't afford to care too much about the cost, but the object does need to go from the initial state to the final state, uh, you can use our method, and within one iteration, it'll get you from the initial state to the final state, but it may not be the best cost solution. Our method also seems to scale well with the number of agents, and this is probably because of the inner problem complexity. So the number of agents only factored in the inner problem. The outer problem is only concerned with optimizing the sort of torque, the resultant torque trajectory. And so it doesn't, the number of agents does not factor into the outer problem at all. It factors into the inner problem, but the inner problem is convex, so it can be solved rapidly. And so that's another nice thing about this bi-level formulation. And because we used a population-based approach, meaning we have many candidate torque trajectories, our solution method was also resistant to convergence failures, restoration failures, things where the optimizer just breaks or just says cannot proceed, you know, Jacobian identical cannot proceed. Like these optimizers just break all the time, especially with the nonlinear baseline. Our method was somewhat resistant to that because it was able to, if one torque trajectory breaks, there are more, and then the genetic operators just produce more. Like we keep the population size constant, and so all torque trajectories in the population would have to break. So that means we would have to get like 50, breaks in a row where the solver just keeps breaking for uh, our solution methodology to not work. So that's a good thing. Our method is resistant to these failures. It will probably not have a catastrophic solver error. And there are some exciting future directions on this work. I know that this first step was using some genetic algorithms, some heuristic methods, population-based methods, but we also have some gradient-based methods in mind. So what if we use the gradient information? In other words, what if we use the information on how the inner problem cost changes when we tweak the torque trajectory? If we're able to use that, gradient, then we could, in theory, change the torque trajectory in exactly the way that it needs to change to improve the problem cost. But calculating that gradient can be expensive. So this is one area that we're exploring right now. Um, the sort of result of that work should come soon in a couple of months. You may see a journal paper on that soon. Hopefully, fingers crossed. And other methods that we want to explore are parallelizing our genetic algorithm, so just making it more computationally efficient, and also using a data-driven or machine learning method to improve that torque trajectory. Because maybe although the torque trajectory outer problem is non-convex, maybe there is a structure to that solution landscape that a data-driven or a supervised learning or a reinforcement learning approach could effectively track into and take less steps and improve the trajectory more and outperform our other methods here. So these are some future directions that we want to explore. Now, that sort of wraps up this problem, and I'll share the link to that paper as part of the links of this presentation. However, just to quickly talk about another problem, a related problem project that we're working on, this one through Manifold. Uh, I'd like to tell you a little bit about the Modular Self-Assembling Space Systems project. So why is this project? This project is in early stages, but I can tell you about the motivation and a little bit about the problem that we're considering. So why is this project important? So what is the future of space structures? There's this thing in space science, in rocketry. It's called the tyranny of the rocket equation. And basically, the problem is that you can't launch things that are very heavy. They have prohibitive fuel costs if you launch very heavy, massive objects. And if we want large space structures, if we want space hotels and space solar arrays, things like this, we can't launch them in one piece. We can't build them on Earth and launch them. That'll be very difficult. Instead, we have to assemble them in space, or even construct them in space, or manufacture them in space. And this is like the motivation of the in-space assembly and manufacturing field, which is becoming more and more popular these days. So I think these slides pretty much just say exactly what I said. Yeah, so there's a demand for large space structures. People want hotels, people want telescopes, um, other infrastructural things like refueling stations. You name it, people want it. They want to put it in orbit. We need large space structures. Okay, so people have proposed a solution to this, which is modular space structures. Now, one quick note, space structures have always been modular. It's just that the modules have been put together by astronauts' hands. They have not been modular in the sense that a single piece can be multifunctional, uh, which is what we want. Okay, so there's a subset of space structure research, which is looking at these voxel-based modular space structures. In other words, modular space structures that are constructed out of the same shaped material, so identically shaped building blocks. If you construct your space structure this way, then it can be reconfigured to serve different functions, and that's what makes this exciting. Um, the function of the space structure can change. Okay, so this is a pretty underexplored area. The sort of way that these companies, so this is a NASA project and this is a European space project. The way that these guys propose reconfiguring the modular structure is by having these inchworm style manipulators that move one piece at a time. And there are other approaches as well in the literature. So some of them assume that the agents or so the modules can pivot on each other electromagnetically. So by using pushing and pulling forces, they can pivot and reconfigure. That research is very cool, but there are it's limited because these blocks don't have an internal sort of thrust or the ability to fly around. And there are other works in this field where people are considering blocks that can fly around so they can sort of detach, fly around, and reconfigure into a new configuration. But the current existing literature assumes very special shapes for this latter category that I just mentioned. So, for example, this paper just came out a few weeks ago, and they're considering this very special fractal shape or a linear shape, and reconfiguring between those two by having the blocks fly around. However, we want more than that. We want a general we want a method to make general shapes, any shape we want, right? Any configuration that we want. So this is sort of the target that we're aiming at with this project is a control algorithm that can take in your desired shape and give you what control inputs each block has to do to make that desired shape, whatever that shape is, whether it has internal cavities, whether it's repeating or not repeating, asymmetric, doesn't matter. That's what we're targeting with this project. So to talk about that, first we just have to talk about one thing, which is how do we even represent like a shape, an arbitrary shape? So let's assume that we have some numbered modules, and let's label the face of each of the modules. So we can use this special structure called adjacent. Sorry, we can use this adjacency matrix. In this case, it's a little bit special, so we'll call it a structure matrix. Special because it just is for this scenario. Adjacency matrix is a general term that's used for any graph. In this case, we're talking about a very specific graph. Therefore, we're calling this the structure matrix. This matrix essentially has a 1 if two faces are connected and a 0 otherwise. And so this is one way. Um, it is very large in 3 dimensions. It would be 6n by 6n. where n is the number of modules, but it's very sparse as well. And there are efficient ways to deal with sparse matrices, large sparse matrices. So this is one way that you can fully sort of capture the structure of a modular system if they're cubes or if they're any polygon, I think, but I actually have to double check that. I'm not sure about that. Okay. One thing that we also have to consider is that when two modules come together, their corresponding part in the structure matrix has to change. And so we have to mathematically represent this somehow. If two faces are within some distance epsilon to each other, then that part of the structure matrix needs to change from a zero into a one. And so with that in mind, we can begin to sort of formalize our problem formulation, but there's more work to do here. So assuming that each module has a thrust, ui, and each also has position, velocity, attitude, and angular velocity, and assuming that the modules are configured according to the structure matrix we just talked about at any given time, then our problem of interest is basically to find thrust trajectories that we can give to the agents such that the dynamics are respected. The structure goes from some initial structure, probably all zeros because all the modules are just free floating, to whatever desired structure we want, the desired terminal structure we want, where all the modules start in whatever their initial starting state is. And there are other important constraints. We still have to formalize these, but this is basically what we're looking at in this project. We're trying to find a way to make this control input where the modules combine together without them colliding in a bad way, without them in a damaging way, without them scraping against each other, without them forming some enclosed space, and then another one needs to get into that enclosed space, but it's too late because the enclosed space has already been made. These sorts of things will factor into our other important constraints that I've put here. Uh, but this is the problem that we're looking at in this project. Okay, so what's next for this project? So of course we'll solve the problem of interest. Um, First, we'll do it in a centralized way, and then we will uh, have a swarm project where we try to find a decentralized algorithm to achieve these shapes, these arbitrary shapes. And then after that, we want to shift away from self-assembly and get towards a swarm assembly, meaning a swarm of agents assembling a modular space structure. So n agents assembling m modules instead of n modules assembling themselves. Um, this is the ultimate sort of direction of this research project at Manifold. Okay, so guys, with that, those are sort of the two things that I want to talk about in this Frontiers call. Thank you so much for those of you who attended. And yeah, the floor is open to any questions. Let me unmute everybody. Um, okay, great. So yeah, any questions? I think I saw one question in the chat from Alex. Let me address that first. So what sort of impact does the attachment point of the agents have on the algorithm? So this is for the original problem, the cooperative transportation problem. And Alex, if you want to add anything to that question, feel free to say something. Otherwise, I'll just address it as it is. Okay. So attachment point meaning these attachment vectors, right? These Q vectors.
Yeah, they got those attachment vectors. That's what I was curious
Gotcha.
about.
Yeah, so they will rotate with the object, and their rotation will be related to the sort of angular velocity of the object in question. But you're right that that is non-convex, right? Because this cross product, these are both variables. So this cross product will be this is a non like affine equality. And so they add like complexity and non-convexity to this scenario. So it's part of the problem, like it's part of the issue that we're trying to deal with. Um, so our algorithm sort of addresses this by if the torque trajectory is defined, then the attitude trajectory is also defined. And the angular velocity trajectory is also defined. And if the angular velocity trajectory is defined, then this becomes affine, right? Because this becomes a constant. So that's like the cheat. Not cheat, but that's what the bi-level formulation is doing to reduce that. Did that answer your question?
Yeah, that does.
Okay, great. One more thing I want to say about that question is that we assume those attachments are completely rigid. We have to make a lot of assumptions to solve any of these problems. Realistically, these attachments would definitely be flexible in some way, and they would add some sort of more horrible dynamics to the scenario. But this is a controls project, not a dynamics project. So the dynamics is a simplified model in a way, in a few ways. Cool. Yeah. Any other questions? Let me go back to that question slide. Wow.
Hey Sid, this is Eunice. First of all,
Hey, Eunice.
uh, uh, school stuff. Yeah, good job.
Thank you.
And
Thank you.
yeah, I just wanted to know, I guess, a little bit on top of what Alex just asked. Do you have any intuition about how the problem would change if you included body dynamics into that? Would it still be solvable? Would it, it would introduce some more complexity, like you said, into the non-convex part of it. So,
Yeah. Yeah. So it would definitely mess up this approach. And the reason for that, I think, is because the decoupling of force and torque would not necessarily be true anymore.
mhm.
And so that would force a modification of this bi-level approach for sure. I don't think that it would be as neat or useful. Um, but maybe that's an interesting like potential extension of this problem. Maybe if you exploited those elastic dynamics in some way, right? Like using some resonance or something like that, then maybe you could find a new efficient way to achieve the objective, right? Uh,
Mhm.
yeah.
And I guess somewhat related to that, when you decompose the problem into the two
Mhm.
sections with the inner and outer problem, um, is there any is there anything fundamental about which part of the problem is convex versus non-convex? So is the translation fundamentally a convex problem, and then the rotational part of it is fundamentally non-convex, or can you flip those two, and it's kind of a
Yeah.
architecture?
Right. So the rotation part is fundamentally non-convex, and this is like a big problem in any spacecraft reorientation. Actually, Alex, if I remember correctly, you used to work on, or you still work on Starlink, and you probably have these like attitude correction problems that you have to deal with. So the attitude dynamics are always non-convex, the torque dynamics. Um, so that will be the non-convex part of this problem. Yeah.
Mhm. Okay, cool. Thank you.
Yeah, no worries. But I will say that a lot of those other approaches that I described at the beginning, they neglect the attitude completely. They just say get the object from point one to point two, point A to point B, which makes the problem much simpler. Attitude control is a big issue with spacecraft. How did you set up the simulation, modeling the dynamics and the attitude? So for the simulation for this project, I just used the equations of motion and I did the forward integration of those equations of motion. So I just sort of did like the state modeling. If we did not use a physically accurate multi-body simulation because my computer was already like burning up from just running the iterative code anyways. So I think that would have cause some major explosions. But that's definitely a part of the extension of this work. I want to use Modelica or something like that to model these multi-body, physically accurate simulations. Cool, guys. Any other questions?
I guess one of the things I was wondering is whether this sort of approach would be able to adapt to, say, like the failure of an agent. Like, say you initially had three agents attached to your irregular object, and then one of
Oh.
them suddenly failed, would it still be able to control the trajectory of the object?
So, like as it is, definitely not because the like right now this is a model predictive like open loop sort of approach, meaning we it's not adaptive in any way, right? Like we're modeling the dynamics and then optimizing the trajectory and yeah, there's no like feedback component right now. But that's an interesting question. Definitely, there could be like a extension of the work where we add an adaptive component. So, okay, we've modeled the optimal trajectory. Now, let's say a failure event happens, right, where one of the agents fails. Um, we maybe set its attachment vector to 0 so that it applies no force and no torque or something like that. Um, or so that wouldn't work, but something like that. We would set its we would force its control to be 0 or something and replan. And in that case, I think that if we had this like event detection and replanning, then yeah, this algorithm would work. We would just have to force that control to be 0 or whatever it is. Maybe it's like firing in a way that it's not supposed to. Whatever that is, we would have to adjust its control externally. So right now, no, but we could modify it so that yes. Okay, awesome. Cool. Any more questions? If not, I'll give a little bit of a closing remarks, closing information. Uh, totally open for questions like in the Discord after this as well. I'm happy to answer anything. Um, or if anybody wants to hop on a call, I can describe whatever. Uh, all right, sweet. Well, guys, thank you so much for attending today. I'm really happy that I was able to talk about this. This work was presented at SciTech this year, but I wasn't able to attend. So actually, you gave me a chance to present this paper that I worked pretty hard on. So thanks for that. Thanks for attending today. If you want to keep up with my work, I have a Google Scholar profile that is going to be more active in the future, I promise. It seems that way. We've got a lot of projects coming, so hopefully that'll start, popping off. And my Twitter, I will also be more active in a research way on there. I'll start sharing more about my work and my papers on there. Of course, you can follow anything manifold related. Well, actually, I'll get to that. You can also follow my LinkedIn or check out my LinkedIn. Um, Same deal there. I'll begin posting some of these papers and things. And so, yeah, you can use any of those three to keep up with my work. However, the modular self-assembling space structures is the next major project that I'm working on. And that is a manifold project, which means you can totally keep up with that project and even join, the conversation on the modular self-assembling space systems channel in our Discord. And then also there will be regular updates in our research log as well on that project. So that Discord channel is already active. You may have already seen some of the activity there. It's been the progress on this project has been pretty fast, and yeah, I think that's a great way to keep up with what I'm up to. Of course, Manifold is also another thing that I'm working on. And so if you want to keep up with Manifold, you can check out our website. I'll share those links after the call. Um, I would like to thank my advisor and my collaborators on this project. I had a few sort of upperclassmen, senior PhD students from my lab who helped me with this, Zahui and Ayush. So thanks to them for all their help in putting together this sort of first PhD project that I worked on. And hopefully there'll be many more in the future. Guys, thanks for attending. Looking forward to seeing you guys in the next one.